When you watch a master pianist play, there is this incredible, almost magical connection between what they hear, what their brain processes, and exactly how hard their fingers strike the keys.
Oh, definitely.
It is just fluid. It is instantaneous.
Yeah, biology really does make it look effortless. You have this completely seamless loop of perception and action, and it's happening in, milliseconds.
Right. But if you actually sit down and try to build a machine to do something even a fraction that complex, say, just reaching out and picking up a cup of coffee without crushing it, that magic completely vanishes.
It really does.
You're suddenly staring at this chaotic mess of physics, electrical noise, and math. Because think about it. Imagine building a robot for a second. How does it actually know where it is?
Exactly.
How do the wheels physically communicate with the central processor? And perhaps most terrifyingly, what happens when the computer tells a motor to do something that is just physically impossible?
Well, you are attempting to replace an entire biological nervous system with, copper wires, silicon chips, and code. And anyone who spends time building robots eventually realizes that the physical world is just notoriously uncooperative.
Oh, I bet.
The math might be absolutely perfect, but reality is messy.
Welcome to the Deep Dive. Our mission today for everyone listening is to demystify mechatronics. We're going to explore exactly how machines perceive the world around them, how their individual parts communicate, and how they translate a sea of raw, really noisy data into precise physical action.
Right, we've got a massive stack of material today.
We really do. We are pulling from industrial sensor selection guides, technical architecture manuals for ROS2 and micro-ROS, data sheets on communication protocols, stuff like I2C, SPI, and CAN bus.
And we're also diving into some advanced research papers on control systems, including some pretty intense real-world case studies on autonomous underwater vehicles and actuator saturation.
Yeah, we are translating all these advanced academic and industrial robotics concepts into everyday understanding. Consider this your ultimate shortcut to being well-informed on how the automated world actually operates under the hood. So, to kick us off, before a machine can take an action, it obviously needs to perceive its environment.
Exactly.
We have to start at the very edge of the robot's physical interface with the physical world.
The sensing layer. And in robotics, we generally divide these senses into two primary categories. The first one is proprioceptive sensing.
Proprioceptive?
Right. This relates entirely to the robot's internal state. So think of joint encoders measuring the exact angle of a robotic arm, or torque sensors measuring how hard a specific motor is working, or even an inertial measurement unit, an IMU, tracking the tilt and orientation of the robot's own body.
Okay, so it sounds like proprioception is basically the robot being self-aware of its own posture.
Yes, exactly that.
Which means the second category must be outward-facing.
Precisely. That is exteroceptive sensing. This is how the robot measures the external environment. So here we are talking about LiDAR systems painting a massive 3D point cloud of a room, or ultrasonic transducers pinging objects to find their distance, and vision cameras taking in complex visual data.
Okay.
And a functional robot absolutely requires both.
Well, let me guess. Proprioceptive data alone cannot tell a robot if it is about to drive off a cliff.
Right.
But exteroceptive data alone cannot tell a robot if its own wheels are actually turning or if they're just, spinning uselessly in the mud.
That is the exact dilemma. You nailed it. A camera might show the hallway moving past, but if the wheel encoders say the wheels are physically locked, the brain knows it is sliding, not driving. You need the internal and external realities to constantly cross-reference each other.
Makes total sense. So let's unpack some of these core sensors to see how they actually capture that reality. Let's start with something exteroceptive, like ultrasonic sensors, because these are fascinating. They function exactly like a bat navigating in the dark using echolocation, right?
The mechanism is completely identical. The sensor emits an ultrasonic pulse. And this is just a sound wave operating at a frequency way above human hearing.
Right.
Once it fires that pulse, it just starts a timer and waits for the echo to return after bouncing off an obstacle.
And because we know the speed of sound through air is roughly, 343 meters per second? The math is incredibly straightforward.
Super simple.
The sensor just measures the round-trip time of that echo, cuts it in half, and calculates exactly how far away the object sits.
It is brilliantly simple, but it does have physical limitations. You have to account for acoustic impedance.
Which is what?
It means soft materials like acoustic foam or heavy fabric, they might just absorb the sound wave completely instead of reflecting it back.
Oh, like yelling into a pillow.
Exactly. Or if the sound hits a hard angled surface, the wave might bounce off into the distance rather than returning to the sensor at all, and that creates a blind spot.
Right, that makes sense. It's like shining a flashlight at a mirror that's angled away from you. You won't see the reflection. But then you scale up to vision systems, which are vastly more complex than just bouncing sound. We constantly hear about CMOS or CCD sensors when talking about cameras. What do those acronyms actually mean in the context of a machine trying to see?
Well, they refer to the physical technology that's actually capturing the light. CCD stands for charge-coupled device, and CMOS stands for complementary metal oxide semiconductor.
That's a mouthful.
It is, and without getting lost in the semiconductor physics, both do essentially the exact same job. They are microscopic grids of silicon pixels that convert incoming photons of light into electrical voltage.
But here's the thing. If you put one of these cameras on a really fast-moving assembly line, you can't just snap a picture the way I do on my smartphone, right? Because if I try to photograph a race car driving by, I just get a blurry streak.
Oh.
And a blurry streak on a factory line means the computer vision algorithm can't read a barcode or inspect a, microscopic solder joint.
Motion blur is the ultimate enemy of industrial computer vision. If a machine is trying to inspect a circuit board flying down a conveyor belt at 3 meters per second, standard photography just fails completely. You have to implement hardware synchronization.
So wait, the camera isn't just recording a continuous video stream and then the software picks the best frame?
Not at all. That takes way too much processing power, and the timing is far too sloppy. Instead, you rely on an external trigger.
Okay.
So you might place a physical proximity laser just up the conveyor belt from the camera. And the instant the leading edge of that circuit board breaks the laser beam, the laser sends a hardware-level electrical interrupt directly into the camera's processor.
Oh, so it just bypasses all the software delays completely?
Yes, it forces the camera to act at that exact millisecond. But catching the moment isn't quite enough. You still have to freeze the motion. To do this, industrial systems use global shutter technology paired with intensely bright microsecond LED flashes.
Okay, so how does a global shutter differ from what is in, say, my iPhone?
Well, most consumer cameras use a rolling shutter. They read the image sensor line by line from top to bottom. It happens fast, sure, but it still takes a few milliseconds.
Right.
If the object is moving incredibly fast, by the time the camera reads the bottom line of pixels, the object has physically moved forward compared to when the top line was read.
Oh, yeah. That causes that weird jello effect you see in videos of airplane propellers, where the blades look all bent and distorted.
The rolling shutter effect. A global shutter solves this by exposing every single pixel on the entire silicon grid at the exact same nanosecond.
Wow.
Combine that simultaneous exposure with an LED strobe light that flashes for perhaps 10 microseconds, dumping a massive amount of light onto the object to eliminate shadows, and you freeze a speeding object with razor-sharp clarity.
It is a perfectly choreographed dance of hardware interrupts and lighting just to take a single clear photo.
It really is.
Now let's pivot inward and look at a proprioceptive sensor, the IMU, or Inertial Measurement Unit. Because these are ubiquitous. They are buried inside our phones, drones, and humanoid robots. The best analogy I can think of is that an IMU is basically the technological equivalent of the human inner ear.
The biological parallel is remarkably accurate.
Because your inner ear is what gives you your sense of balance. The fluid moving through those tiny canals tells your brain which way is down and whether you're spinning, tilting, or falling. You can close your eyes in a pitch-black room, and you still generally know your orientation. An IMU does the exact same thing for a machine, right? It senses tilt and rotation without needing to see anything external.
Yes, and it accomplishes this by packaging two different instruments together, accelerometers and gyroscopes.
Okay.
Accelerometers measure linear movement and the constant downward pull of gravity. Gyroscopes measure rotational velocity, how fast the sensor is spinning around its own axis.
But how do they physically do that on a microscopic computer chip? I mean, you can't put a traditional spinning metal top inside a smartphone.
No, you definitely can't. You use MEMS technology, microelectromechanical systems.
MEMS.
Right. Inside that tiny black square on a circuit board, engineers have etched microscopic physical structures out of silicon. For an accelerometer, imagine a microscopic comb made of silicon, where the teeth of the comb are interleaved with another set of fixed teeth.
Okay, I'm picturing it.
And the movable comb is suspended on microscopic silicon springs.
So when the robot accelerates forward, inertia causes that suspended comb to lag behind for a fraction of a second, moving closer to the fixed teeth.
Yes. And as those silicon teeth move microscopically closer together, the electrical capacitance between them changes. The chip measures that minute change in capacitance and calculates the physical acceleration.
That is wild.
But here's the catch. The robot's brain does not understand silicon springs or capacitance. It only understands digital data.
Just ones and zeros.
Exactly. And what's fascinating here is the signal acquisition and conditioning phase. This brings us to the foundational bottleneck of all robotics, the analog to digital converter, or ADC. Every physical phenomenon, whether it is the photon flux hitting a CMO sensor, the acoustic echo hitting a microphone, or the capacitance shifting in an IMU, must be translated into a digital number. And this introduces the technical concept of resolution.
Right, because resolution dictates the baseline precision of your entire system. If the ADC isn't sensitive enough, the robot is effectively numb to small changes.
Exactly. Let's use a rotary encoder as an example to define resolution. An encoder measures the angle of a spinning shaft, like a robot arm joint. A 12-bit encoder produces 4,096 distinct digital position values for a single 360-degree revolution.
Okay, so that means it can detect a movement as small as 0.08 degrees. That actually sounds incredibly accurate.
It is decent, but if you upgrade your hardware to a 16-bit encoder, it produces 65,536 distinct position values per revolution. Yeah, by adding just 4 more bits of data width, you get a massive 16-fold improvement in precision. You are slicing that exact same 360-degree pie into 65,000 microscopic pieces.
Well, wait. If more resolution gives the robot a finer sense of touch and movement, why wouldn't engineers just put 24-bit ultra-high-resolution sensors on every single joint of every single machine? Just give the factory line superhuman perception across the board.
Because in industrial engineering, precision is only one variable in a highly constrained equation. You have to balance that mathematical precision against financial cost, environmental durability, and functional safety. High resolution often comes with heightened fragility or just crippling expense.
Which brings us to the great encoder dilemma. When an engineer is choosing the right sense for a machine, they are constantly making trade-offs. So let's dig into that cost versus need trade-off by comparing the two main architectures of rotary encoders, incremental and absolute.
Right. An incremental encoder is the workhorse of basic automation. It is relatively simple and budget-friendly because it only measures changes in motion. As the shaft spins, an internal photoelectric sensor reads a spinning glass disc with tiny slots cut into it. Every time a slot passes the sensor, it generates an electrical pulse.
But if it's just generating identical pulses over and over, how does the machine know if the shaft is spinning clockwise or counterclockwise?
It uses something called quadrature encoding. It actually has 2 sensors, usually called the A phase and the B phase, and they are positioned slightly offset from each other.
Okay.
Because of this offset, if the shaft spins clockwise, the A pulse triggers just before the B pulse. If it spins counterclockwise, the B pulse triggers first. The microcontroller just looks at which signal arrived first to determine the direction. And it also usually has a Z-index pulse, which triggers exactly once per revolution to act as a reference marker.
But the major catch here is that incremental encoders have zero memory, right?
Yeah.
If the factory loses power, the incremental encoder goes dead. When the power comes back on, it has no idea what angle the robot arm is currently resting at. It just sets its current position to 0.
Right. And to fix that, the robot has to perform a physical homing routine. It has to slowly and blindly move its arm until it physically bumps into a hard limit switch wired into the frame. Only then can it say, I hit the limit switch, I know exactly where I am now, and resume normal operations.
It's like waking up in a pitch-black hotel room. You have to carefully slide your hand along the wall until you find the door frame to orient yourself.
That's a great way to picture it.
Now compare that to an absolute encoder.
Absolute encoders use a vastly more complex internal disk. Instead of a simple ring of identical slots, the disk is etched with multiple concentric rings of complex patterns. Every single microscopic angle of rotation maps to a completely unique digital disk.
I read an analogy in the sources comparing incremental encoders to Snapchat stories. As soon as the app closes or power drops, the history is gone forever. But absolute encoders are like a permanent iCloud backup. They remember everything because the physical pattern on the disk represents the exact location at all times.
Exactly. And there is a brilliant piece of computer science hidden inside absolute encoders. They don't use standard binary counting to pattern those disks. They use something called gray code.
Wait, why not standard binary? I mean, computers love binary.
Because standard binary is physically dangerous in a sensor.
Dangerous? How?
Think about the number 7 in binary. 0, 1, 11. And then number 8 is 1000. To move from position 7 to position 8, all 4 physical bits have to change state simultaneously.
Okay.
If the sensor is moving quickly and the tiny light beams reading those slots are misaligned by even a fraction of a millimeter, the sensor might accidentally read 11,111 for a microsecond before settling on 1000.
Oh, and a microsecond reading of 1111 means the robot thinks it just teleported to position 15.
Right, which would cause the motor to panic and jerk wildly.
That is terrifying.
It is. So gray code is a specialized binary system where only a single bit changes state between any 2 consecutive numbers. Going from position 7 to 8 might look like changing 0100 to 1100. Because only one optical slot changes at a time, those dangerous mid-transition glitches are mathematically impossible.
That is an incredible detail. But all that etched complexity means absolute encoders carry a massive price premium. If I'm just tracking the speed of a luggage conveyor belt at an airport, an incremental encoder is perfectly fine. I don't care what exact angle the belt wheel stopped at, as long as I know how fast it accelerates when the motor turns back on.
Exactly. But if you are controlling a multi-million-dollar robotic surgical arm performing a delicate operation, it absolutely cannot afford to guess where it is or perform a blind homing routine into a patient's chest when the system boots up.
Oh, wow, yeah. No homing routines in surgery.
Right. You pay the massive premium for absolute encoders.
Beyond cost, engineers also have to evaluate environmental durability. A sensor living in a pristine, climate-controlled laboratory has a very easy life. But an industrial sensor might be bolted to an offshore oil rig.
And in those environments, the IP rating ingress protection against dust and water and chemical durability of the housing are vastly more critical than an extra 4 bits of resolution. If your sensor is measuring caustic fluid flow in a chemical plant, a 24-bit sensor is useless if the housing dissolves in a week.
The linearity of the sensor is also a crucial criteria we found in the source guides. What does linearity actually mean in practice?
Linearity is the consistency of measurement error across the entire sensing range. Imagine a temperature sensor. If it reads 20 degrees perfectly, but when the real temperature hits 100 degrees, the sensor starts reporting 110 degrees because its internal components warp under heat, that sensor has poor linearity.
Oh, I see.
You want a sensor that scales its readings in a perfectly straight, predictable line from its minimum to its maximum operating limits.
Makes sense. And finally, we have functional safety. This is a domain of international standards like ISO 138491. And from what I gather, this is less about making sure the robot does its job and more about making sure the robot doesn't crush a human operator when a component inevitably fails.
Absolutely. Industrial robots possess terrifying amounts of kinetic energy. The ISO standard mandates that safety-critical sensing functions, like a laser curtain detecting if a human has walked into the work zone, must achieve specific safety performance levels. A common requirement is Performance Level D, or PLD.
And you cannot achieve performance level D just by buying one really expensive high-quality sensor, right?
Okay.
The standard does not trust single points of failure.
No, it doesn't. The math of probability dictates that eventually every sensor fails. To achieve PLD, you must implement redundant sensing channels. You need 2 completely independent sensors, often using different physical technologies, monitoring the exact same physical zone.
Right.
And they both wire back to a safety relay that constantly cross-checks their data.
So if the primary laser scanner says the zone is clear, but the backup radar sensor detects a human, the safety relay instantly assumes the worst and trips the emergency brakes, shutting the machinery down.
Exactly. It fails safely. So at this point, our engineer has carefully selected the perfect sensor. It has the right resolution, the ideal gray code absolute memory, and rugged environmental housing. It is successfully measuring the physical world.
But all of that carefully gathered data is completely useless if it just sits trapped inside the sensor. The digital ones and zeros have to physically travel over a wire to the robot's brain, the microcontroller.
And this introduces the absolute nightmare of physical wiring and communication protocols, getting the sensors to talk without shouting over each other.
Let's break down the physical reality of how these connections actually work. The 3 dominant protocols in mechatronics are I2C, SPI, and CAN bus. Let's start with I2C, which stands for Inter-Integrated Circuit.
Right. I2C is incredibly popular for connecting multiple, simple, low-speed sensors to a single microcontroller. It is a 2-wire bus system. You have 1 wire for the clock signal, called SCL, which acts like a metronome keeping everyone's timing synchronized. And the other wire is for the data, called SDA.
You know, the best way I can visualize I2C is like a classroom full of students. The microcontroller is the teacher, and all the sensors are the students.
Okay, I like this.
There is only one single piece of paper being passed around the room for notes. If the teacher wants a temperature reading, they write a note addressed specifically to the temperature sensor's ID and pass it down the line. The temperature sensor reads it, writes the answer on the same paper, and passes it back. All the other sensors ignore the note because it isn't addressed to them.
That classroom analogy highlights the core benefit perfectly. Because every device shares the exact same two wires, it keeps the physical wiring harness on a circuit board incredibly clean and simple. You don't have wires crisscrossing everywhere. But sharing a single data wire introduces a unique hardware requirement. Well, I2C devices don't actually push voltage onto the wire to send a logical 1. They only pull the voltage down to ground to send a logical 0.
Wait, if they only pull the voltage down, how does the wire ever get back up to send a 1?
Through a physical component called a pull-up resistor. This resistor connects the data line to the main power supply. When no sensor is actively pulling the line down to ground, the resistor passively pulls the voltage back up to a 1.
It's basically a spring pulling a heavy door closed. When a sensor wants to send a 0, it acts like a person pushing the door open against the spring. When it lets go, the spring pulls the door shut again to send a 1.
Yes. And sizing that spring, calculating the exact ohm value for that pull-up resistor is a delicate millimeter war of printed circuit board, or PCB, design. It all comes down to bus capacitance.
Capacitance is basically the wire's natural tendency to act like a sponge for electricity, right?
Exactly. Physical wires have mass, and they absorb a tiny bit of charge before the voltage actually rises. It is like trying to pressurize a water hose. The hose expands slightly before the water shoots out the other end. That delay is dictated by the RC time constant resistance multiplied by capacitance.
Let's look at a concrete engineering example from the source math. Say you are building a system with a standard 5-volt power supply. The physical length of the wires creates a bus capacitance of 150 picofarads. You have 3 sensors connected. If you choose a pull-up resistor that is too weak, say 10,000 ohms, what happens?
Well, the spring isn't strong enough to quickly overcome the sponge of the capacitance. When the sensor lets go of the line, the voltage doesn't snap instantly back up to 5 volts. It slowly, sluggishly crawls upward.
Oh, bad news for digital signals.
Very bad. If you looked at it on an oscilloscope, instead of a sharp, crisp, square wave representing 1s and 0s, you would see sloppy, slooping shark fins. The fast-paced digital signals blur together, and the microcontroller gets completely corrupted data.
So the instinct would be to use a massive, super strong pull-up resistor, like 100 ohms, to violently yank the voltage back up and keep the signals crisp, right?
You'd think so, but if you do that, the spring is so strong that the tiny transistors inside the microscopic sensors don't have the electrical strength to push the door open. They try to pull the voltage down to ground, but the 100-ohm resistor fights them, and the voltage never drops low enough for the microcontroller to register as 0 ohm.
Wow.
The math for this specific 5-volt, 150 picofarad scenario dictates a rigid window. A minimum resistance of roughly 511 ohms to ensure the devices can pull down, and a maximum of 909 ohms to ensure the signal rise times don't turn into shark fins.
So the electrical engineer settles right in the middle, likely soldering a standard 680 ohm resistor onto the board. It is stunning that a microscopic 2-cent component entirely dictates whether a sophisticated robot brain can even hear its own senses.
It really is. But what if the classroom note passing of I2C is just fundamentally too slow for your application? That is where you upgrade to SPI, Serial Peripheral Interface.
Right, SPI is built for speed. It easily hits 10 to 20 megabits per second, or much higher, but it achieves that speed by brute forcing the wiring. It expands from 2 wires to a 4-wire system.
Exactly. You have a clock wire, a wire for master out, slave in, where the brain talks to the sensor, and a wire for master and slave out, where the sensor talks back. Because they have dedicated directional wires, they can talk over each other simultaneously in full duplex mode.
So if I2C is passing a single node around the classroom, SPI is like the boss of a company having dedicated private telephone lines wired directly to every single employee's desk. The boss can demand data instantly.
Yeah.
But there's a 4th wire, right? The chip select wire.
Yeah, that is the Achilles heel of SPI. Because there is no addressing system like the IDs on I2C, the microcontroller needs a physical way to tell a specific sensor to pick up the phone. It does this by dropping the voltage on a dedicated chip select wire connected exclusively to that single sensor.
Which means every time I add a new sensor to the SPI bus, I have to run a brand new dedicated physical wire all the way from the brain to that sensor.
Yep.
If I have 20 sensors on a robotic arm, my wiring harness starts to look like a spaghetti monster.
It does, and it creates unacceptable weight, complexity, and points of physical failure. If you connect this to the bigger picture, like if you were building a modern automobile, you want to minimize the weight of copper wire to improve fuel efficiency. You cannot run dedicated SPI lines to the dozens of sensors scattered from the bumper to the taillights.
And that perfectly transitions us to the undisputed king of industrial and automotive communication,
Right.
the CAN bus, Controller Area Network.
Yes. CAN bus was developed by Bosch in the 1980s, specifically for the incredibly harsh, electrically noisy environment of a vehicle engine bay. It returns to a two-wire system, but it uses a brilliant concept called differential signaling on wires labeled CAN high and CAN low.
So how does differential signaling defeat electrical noise? Say the wire runs right past a massive alternator that is blasting out electromagnetic interference.
Well, instead of sending a voltage relative to ground, CAN bus sends signals by changing the voltage difference between the two wires. To send a bit, CAN high might jump up to 3.5 volts, while CAN low drops to 1.5 volts.
Okay.
The receiver doesn't care about the absolute voltage. It only cares that the difference between the two wires is exactly 2 volts.
So if that massive alternator fires and sends a 5-volt magnetic spike into the wiring harness, it hits both wires equally. CAN high gets pushed from 3.5 to 8.5 volts, and CAN low gets pushed from 1.5 to 6.5 volts.
Exactly. And 8.5 minus 6.5 is still exactly 2 volts. The receiver subtracts the lines, the 5-volt noise spike is mathematically erased, and the pristine digital signal emerges completely unscathed.
That is incredibly elegant. But CAN bus doesn't have a master controller like SPI or I2C. How do the nodes coordinate without talking over each other? I imagine like a crowded, noisy meeting room full of executives, but there is no CEO present to act as the moderator.
Anyone can speak whenever they want, but they strictly obey a priority system based on their message IDs through a process called arbitration. In CAN bus, a logical zero bron is a dominant voltage state, and a logical 1 is a recessive state.
So a 0 physically overpowers a 1 on the wire.
Yes. When a node starts transmitting, it broadcasts its message ID bit by bit while simultaneously listening to the wire. Let's say the engine temperature sensor and the emergency brake sensor both try to shout at the exact same millisecond.
The brake sensor obviously have the more urgent ID, which would be loaded with dominant zeros.
Right. They both send their first few bits, and the bits match. But then, the temp sensor tries to send a recessive 1, while the brake sensor sends a dominant 0. The physical wire drops to the dominant 0 state.
And because the temp sensor is listening to the wire while it talks, it expects to see the 1 it just sent, but it sees the 0 instead.
It instantly realizes someone with a higher priority is talking. The temp sensor immediately shuts up, drops off the bus, and waits for the message to finish. The urgent brake message continues without losing a single microsecond to a collision. The network inherently moderates itself through physical physics.
It also has robust error checking, doesn't it? It uses CRCs, or cyclic redundancy checks. I've always wondered how a CRC actually catches a corrupted bit.
Conceptually, it is like polynomial long division. The sending sensor takes the entire block of data it wants to send, treats it as one giant binary number, and divides it by a pre-agreed mathematical divisor. It takes the remainder of that division, the CRC value, and tacks it onto the end of the message.
So when the microcontroller receives the message, it performs the exact same long division. If a random noise spike managed to flip a single bit from a 0 to a 1 in transit, the division will produce a completely different remainder.
Exactly.
The microcontroller sees the remainders don't match, knows the data is corrupted, and instantly throws it in the trash.
Yep. And to protect all this high-speed data, CAN bus requires 120 ohm termination resistors at the physical ends of the main wire trunk. High-frequency electrical signals act like physical waves. If they hit the abrupt end of an unterminated copper wire, they bounce back, echoing down the line and colliding with new incoming signals, completely destroying the data.
So the 120 ohm resistors act like acoustic foam, absorbing the electrical energy at the ends of the bus so there are no reflections.
Perfect analogy, yes.
So to summarize the journey so far for you listening, the physical world has been measured by our sensors. The analog phenomena have been digitized by the ADC into crisp 1s and 0s. The data has survived the chaotic, noisy journey across the differential CAN bus wires. It has finally arrived at the brain, the microcontroller. The brain knows everything.
Unfortunately, no.
Wait, really?
The brain has the data, but the raw data is a liar. The real world is relentlessly messy. We are now entering the realm of mathematical filtering and sensor fusion.
Let's define what we mean by signal noise in this context. Because imagine a mobile robot tasked with delivering parts across a factory floor. To the human eye, that concrete floor looks perfectly flat and smooth. But at a macroscopic level, it is covered in tiny bumps, microscopic cracks, and the vibration of heavy machinery nearby.
Oh, yeah. If you look at the raw data streaming in from the robot's proprioceptive accelerometer as it drives, it isn't a smooth, clean line indicating forward movement. It looks like a jagged, wildly spiking heartbeat monitor. The tiny, high-frequency physical vibrations of the hard rubber wheels chattering against the concrete create massive, instantaneous spikes in the acceleration readings.
It completely masks the true, purposeful, low-frequency movement of the robot. If the microcontroller tries to react to every single one of those jagged spikes, the robot will literally vibrate itself to pieces, trying to steer out of microscopic potholes that don't actually matter.
That jagged artifact is signal noise. The microcontroller must use mathematical filters to scrub the noise and find the underlying truth. But external noise isn't the only problem. The sensors themselves have internal, hidden flaws. Gyroscopes, for instance, suffer from a terrifying phenomenon called angle random walk, or ARW.
Angle random walk, that sounds like a drunk person trying to walk in a straight line.
It is a highly accurate description. An IMU calculates its orientation through integration. It constantly adds up tiny changes in rotation over time to figure out where it is pointing. I turned 1 degree left, then 2 degrees right, so I am 1 degree right of my starting point.
But no electronic sensor is perfect. There is an inherent microscopic floor of white noise in the sensor's electronics, caused by, thermal fluctuations in the silicon.
Exactly. So every time the gyroscope adds up a measurement, it accidentally includes a tiny fraction of a degree of that thermal white noise. Because it is constantly summing these measurements thousands of times a second, those microscopic errors permanently compound.
So over seconds and minutes, the IMU's mathematical understanding of straight ahead slowly drifts away from physical reality. If an autonomous drone flies into a tunnel, loses its GPS signal, and has to navigate purely by dead reckoning using its IMU, the angle random walk will eventually cause it to veer completely off course and crash into the tunnel wall.
It is an error you cannot simply calibrate away at the factory. It is baked into the fundamental physics of the sensor. So the bumpy floor is tricking the accelerometer with high-frequency noise, and the angle random walk is tricking the gyroscope with low-frequency drift. How does a robot know what to trust?
This is where sensor fusion comes in. The brain stops relying on a single source of truth and blends multiple flawed senses together to create one reliable, unified worldview.
The simplest, most elegant method for this is the complementary filter. It is a computationally cheap algorithm that operates in the frequency domain. It essentially says, I know the gyroscope is incredibly fast and accurate for quick, sudden dynamic movements, but it drifts over long periods of time. Conversely, the accelerometer is incredibly noisy during quick movements, but over a long period of time, it always knows exactly which way gravity is pulling.
So the complementary filter acts as a dual gatekeeper. It uses a high-pass filter to only trust the gyroscope for short-term, high-frequency changes. And it uses a low-pass filter to trust the accelerometer as a long-term, low-frequency anchor, constantly pulling the gyroscope's baseline back to the reality of gravity, permanently canceling out that angle random walk drift.
It is brilliant for simple robots. But when a complementary filter isn't enough, when you are dealing with nonlinear dynamics, extreme speeds, or mission-critical aerospace applications, engineers turn to the heavy artillery, the Kalman filter.
The Kalman filter is legendary. It is the math that helped stabilize the Apollo missions so they could land on the moon. How does it actually work?
A Kalman filter is fundamentally different from a standard filter because it is a predictive algorithm. It doesn't just passively look at the current sensor readings. It maintains a complex internal mathematical model of the robot's physical dynamics. It constantly calculates 2 steps: the prediction step and the update step.
So in the prediction step, it uses the laws of physics to guess the future. It says, given how fast my wheels were turning a millisecond ago, and knowing my own mass and inertia, I predict I should be exactly 1 inch further forward right now.
Exactly. Then comes the update step. The actual noisy sensor data arrives. The sensors might claim the robot is 1.1 inches further forward. The Kalman filter calculates the innovation, the difference between the prediction and the measurement.
Okay.
It then uses complex probability matrices to decide how much to trust its own prediction versus how much to trust the noisy sensors, dynamically blending them to find the most statistically probable truth.
I read in the research about an incredibly modern evolution of this called the soft-switching adaptive Kalman filter, which was specifically developed for aerospace platforms using magneto-hydrodynamic sensors. That is a massive string of buzzwords. What does it actually do differently?
Normally, a Kalman filter's stress levels, its tuning parameters, are relatively fixed. But imagine a fighter jet or a supersonic drone hitting a pocket of extreme turbulence, or experiencing the physical shockwave of an explosion. A specific sensor might suddenly become wildly, dangerously unreliable for a fraction of a second.
And a standard Kalman filter might try to incorporate that massive error spike, throwing off the whole prediction.
Right. The SOX switching adaptive Kalman filter constantly monitors the statistical health of the incoming data. If it detects an anomalous overrange shock that violates the expected probability, it dynamically adjusts the fusion weights on the fly. It mathematically scales something called the measurement noise covariance matrix.
Which is a fancy way of telling the brain, the accelerometer is currently screaming nonsense because of a shock wave. Ignore it completely for the next 10 milliseconds and rely entirely on my internal prediction and the gyroscopes until the ringing stops.
It is like squinting your eyes and relying on your memory of the room when a bright flashbang goes off so you don't lose your balance. It is breathtaking mathematics.
It really is. So let's take stock. The brain has successfully gathered the data over the CAN bus. It has filtered the jagged noise. It has mathematically fused the flawed sensors using predictive Kalman matrices. It knows exactly what is happening in the physical world with absolute certainty. Now, finally, it must command the physical motors to react. We are moving from perception to action.
This requires a closed control loop. And the absolute foundational bedrock of nearly all industrial control loops is the PID controller: proportional, integral, and derivative.
The history here is fascinating. The PID controller dates all the way back to 1922, formalized by a Russian-American engineer named Nicholas Minorsky. He was trying to design automatic steering systems for massive U.S. Navy battleships. Over a century later, his math still runs the vast majority of the world's automated systems, from cruise control to industrial heaters.
It is incredibly robust. To understand why it works so well, let's use a grounded analogy. Imagine you are driving a car on the highway, and your goal is to stay exactly in the center of your lane.
Okay, I'm driving. The center of the lane is my set point. The distance I have drifted to the left or right of center is my error.
The proportional term of the PID loop is your immediate reaction to that error. If you drift slightly to the left, you turn the steering wheel slightly to the right. If you hit a patch of ice and slide way over toward the rumble strip, your error is massive, so your proportional response is massive. You yank the steering wheel hard to get back. The proportional response is strictly multiplied by the size of the current error.
But if I only use a proportional response, I am going to have a terrible time. As I yank the wheel and my car rushes back toward the center of the lane, the error decreases, so I loosen the wheel. But my car has momentum and mass. If I don't actively countersteer, that momentum will carry me right across the center line and into the opposite lane. I will oscillate back and forth, swerving down the highway forever.
That is exactly where the derivative term comes in. The derivative looks at the rate of change of your error. It sees that your error is shrinking very quickly. It acts like a mathematical crystal ball, predicting the immediate future, or more accurately, it acts as a brake.
So the derivative tells me to actively ease off the steering wheel, or even countersteer slightly, before I reach the center line. It dampens the proportional response, allowing the car to slide smoothly and asymptotically into the dead center of the lane without overshooting.
So we have P for the present and D for the immediate future. What about the integral?
The integral handles persistent, hidden biases. Imagine my car has a poorly aligned front tire, or there is a strong, constant crosswind blowing from the left. The proportional and derivative controllers might fight the wind, but they require an error to generate a steering force.
Right.
So you end up stabilizing just slightly off-center, riding the right edge of the lane, because you constantly need that tiny bit of proportional error to justify keeping the steering wheel turned against the wind. That is called a steady-state error.
The integral term looks at the deep history of the error. It constantly sums up the error over time. It realizes, wait, we have been 2 inches to the right of the center line for the last 60 seconds. This isn't a temporary bump. This is a systemic bias. As the seconds tick by, the integral slowly builds up a massive backlog of accumulated correction, eventually generating enough distinct mathematical force to push the car perfectly back to dead center, completely nullifying the crosswind.
Proportional for the present, derivative for the future, integral for the past. It is an incredibly elegant, rock-solid loop. But as beautiful as a single PID loop is, modern robotics has moved far beyond it. You can't run a bipedal humanoid robot just by wiring up 40 independent PID loops.
No, you really can't. A simple PID loop handles one variable, like the speed of a single motor. But a modern autonomous mobile platform has dozens of interlinked motors, lidars, cameras, and navigation algorithms. You need a grand conductor to manage the entire symphony. That is what ROS2, the robot operating system, provides.
And drilling down into the technical architecture from the manuals, the architecture relies heavily on a framework within ROS2 called ROS2 control.
ROS2 control is a masterclass in abstraction. It hides the messy, hardware-specific reality of the physical robot away from the high-level brain. It introduces concepts called hardware interfaces and a controller manager.
What do those do?
Well, the hardware interface is a specialized C++ class that acts as the sole translator for a specific physical motor or sensor. It exposes standardized state interfaces, which are read-only variables like the current physical angle of a joint, and command interfaces, which are handles you can write to, like commanding a specific torque to the motor.
And the controller manager acts as the bouncer. It oversees all these interfaces, ensuring that only one high-level algorithm can claim a command interface at a time. It prevents a scenario where the autonomous navigation algorithm tells the wheels to drive forward, while the emergency collision avoidance algorithm simultaneously tells the wheels to drive backward, which would just fry the motor drivers.
The most critical aspect of this ROS2 architecture is the strict requirement for real-time deterministic execution. When you write a C++ hardware interface for ROS2 control, you are operating in a real-time loop that must execute hundreds or thousands of times a second with absolutely zero jitter.
Which means you are forbidden from using standard programming practices like dynamic memory allocation. You can't suddenly ask the computer's operating system to give you a new chunk of RAM to store a variable while the control loop is running.
Because asking a standard operating system like Windows or Linux for memory is a non-deterministic process. The OS might take 1 microsecond to find the RAM, or it might decide to pause your program for 50 milliseconds while it handles a background network update.
Oh, wow.
In the software world, 50 milliseconds is unnoticeable. In the robotics world, a 50 millisecond blocking call means your bipedal robot's balance loop completely pauses, gravity takes over, and the robot falls flat on its face.
Yeah.
The code must be pre-allocated and perfectly deterministic.
And this constraint becomes even more extreme when you push this architecture down to micro-ROS. Micro-ROS is an initiative to put the ROS2 framework onto tiny, resource-constrained microcontrollers embedded right next to the sensors. When engineers configure network communication in micro-ROS for high-frequency sensor data, they have to make choices about quality of service, or QoS. They intentionally prioritize best effort communication over reliable mode.
That sounds completely counterintuitive to a layperson. Why would an engineer intentionally choose an unreliable connection for critical sensor data?
Because reliable mode, which acts like a TCP network connection, requires the receiver to send an acknowledgement packet back saying, "I got the message." If the network is busy or noisy, the sender blocks and waits and might even try to resend the old data. In a high-frequency control loop, waiting is death. Old data is toxic.
Exactly. Best effort mode acts like a UDP connection. It just fires the data packets into the void as fast as physically possible and immediately moves on. If a packet of wheel velocity data drops due to electrical noise, who cares? The controller doesn't want the old data anyway because a completely fresh, updated packet is arriving in 2 milliseconds regardless. You prioritize the ruthless flow of current time over the perfect reliability of the past.
All right, we've covered the sensors, the communication layers, the Kalman filtering, and the control theory of PID and ROS2. Everything we have discussed so far is fundamentally based on a major assumption, that the physical hardware will actually do what the pristine math commands it to do. But for this next section, we have to look at what happens when physics flat out refuses to cooperate.
The math exists in a perfect vacuum. The hardware exists in a universe of friction, heat, and physical limits.
I want to try something different here. I want you to step out of the calm, analytical expert persona. Put on a hard hat. Imagine you are a seasoned, battle-tested field engineer who has spent 20 years in industrial plants watching multi-million-dollar hardware literally tear itself apart because of mathematical oversights. Talk to me from the trenches. What is the most terrifying reality you actually deal with?
You want to know what keeps field engineers awake at night? It isn't a software bug. It's actuator limitations. It is the brutal reality of saturation. You can write the most beautiful, mathematically perfect PID algorithm in the world. A gust of wind hits your heavy lift drone, and the PID math instantly calculates that the motor needs to spin at 15,000 RPM to keep the drone level. But the physical motor, the copper and magnets, has a hard maximum limit of 10,000 RPM.
Wow.
That is amplitude saturation. The math is screaming for 150% power, but the physical hardware is maxed out at 100%. The system is starved of the physical energy it needs to follow the mathematical trajectory.
That sounds dangerous. But at least the motor is giving it everything it has. But what about rate saturation?
Rate saturation is the silent killer. It is insidious. Imagine that same drone motor is currently hovering, spinning at 2,000 RPM. The wind hits and the math commands it to jump to 10,000 RPM. The amplitude limit is fine. 10,000 is within the motor's absolute capability, but the math expects the motor to reach 10,000 RPM instantly.
Right.
Physics dictates inertia. A heavy physical rotor takes physical time to spool up. It might take 2 full seconds to accelerate. The math updates every millisecond, expecting the thrust to be there, but the hardware lags horribly behind. The control loop loses its mind because the physical reality is fundamentally decoupled from the mathematical prediction.
So what actually happens inside the PID loop when saturation hits? The math is asking for the impossible. Does it just give up?
It does something much worse. It triggers a catastrophic chain reaction called integrator windup. Let's go back to your driving analogy. Imagine your car gets its front bumper wedged tightly against a solid concrete barrier. You are pushing the gas pedal to move forward, but the wall stops you dead. You have a massive error. You aren't moving toward your set point.
Right, my set point is 20 feet ahead, but my actual position is locked.
Your proportional term maxes out the gas pedal. Your motor is heavily saturated against the wall. But remember the integral term, the one that counts up past errors. While you sit there idling against the wall, the integral is silently ticking up. Every millisecond, it is adding up the massive position error. 1 second, 2 seconds, 10 seconds pass. The integral builds a gargantuan, terrifying mathematical backlog of required correction. It is screaming inside the computer to apply 10 million pounds of forward thrust.
But the wall is still in the way, so nothing happens.
Exactly. Nothing happens until, imagine the wall suddenly vanishes, or the forklift blocking your path backs up.
Oh no, the car is suddenly free to move.
The physical obstruction is gone. Your motor is suddenly unimpeded, but your integral term is still holding that massive, wound-up sum of historical error. The car doesn't just drive forward normally. The accumulated integral force launches it like a missile. It violently and uncontrollably overshoots the target. In a drone, wind-up causes it to flip upside down and plow into the concrete the second a gust of wind stops. I've seen it in industrial boiler systems. A pressure valve gets physically jammed shut. The integral winds up the heater to maximum. A worker taps the valve with a wrench, it unjams, and the wound-up system instantly vaporizes the water, triggering a catastrophic pressure explosion. That is integrator windup.
The history of control theory is littered with real-world examples of this. There is a famous, sobering paper from our research by an engineer named Günther Stein titled Respect the Unstable.
Every control engineer reads Stein's paper. It is practically mandatory. He meticulously documented how ignoring rate saturation and windup caused tragic, high-profile failures in unstable systems. He analyzed the early flight tests of the Ansabe Gripen fighter jet, which crashed spectacularly because the flight control surface is rate saturated. The hydraulics physically couldn't move the flaps as fast as the unstable aerodynamics required.
Incredible.
He looked at the YF-22 prototype crash for similar reasons. He even traced elements of control saturation and windup down to the contributing factors of the Chernobyl nuclear disaster. When you tell highly unstable physical systems to do something they cannot physically execute, the math winds up and the physics breaks violently.
Let's step back into the lab. How do you actually solve this? How do engineers stop the math from winding up when the hardware inevitably maxes out?
In the engineering world, you face a stark architectural trade-off between highly complex modern anti-windup, known as MOW, and simple, elegant, classical anti-windup, or COW.
Let's look at modern anti-windup first.
MAW relies heavily on something called Model Predictive Control, or MPC. MPC is a computationally heavy behemoth. It requires the microcontroller to hold a perfect, exhaustive mathematical model of every physical constraint of the robot. The algorithm doesn't just look at the present, it constantly looks into the future, calculating thousands of possible movement trajectories, and actively avoids commanding any action that would eventually violate the amplitude or rate limits of the hardware. It is theoretically perfect. It preemptively dodges saturation.
It sounds like a supercomputer playing chess against physics.
Yeah.
But I imagine the computing power required is massive.
It is overwhelming. You cannot run a complex multivariable MPC algorithm on a tiny $5 microcontroller embedded in a robotic wrist joint. It takes too long to compute the matrix math. It causes latency, which destabilizes the loop.
Which brings us to classical anti-windup, CAW.
Classical anti-windup is a triumph of engineering simplicity. Instead of running a massive predictive physics simulation, it simply watches the physical actuator. The most effective method is called integrator resetting or back calculation.
How does back calculation actually work mathematically?
The algorithm simply compares the theoretical command the PID loop generated against the actual physical output limit of the motor. If the PID math asks for 15,000 RPM, but the motor controller reports it is physically capped at 10,000 RPM, the algorithm detects that 5,000 RPM discrepancy.
Yeah.
It takes that exact mathematical discrepancy and feeds it backwards directly into the integral term, mathematically subtracting it from the running sum.
So it is actively bleeding off the windup pressure exactly as fast as it builds up. The integral is never allowed to accumulate an error that the motor can't physically act upon. The math is forcibly tethered to the physical reality.
Precisely. There are specific algorithms for this, notably LQIIW, which stands for Linear Quadratic Integral with Anti-Windup and PDW. And the benchmark testing on these is fascinating. Researchers ran trials testing these classical algorithms on the yaw control of a Remus autonomous underwater vehicle, an AUV.
Controlling a submarine sounds like a nightmare for rate saturation. Water is incredibly dense, so the sub's physical dynamics are sluggish. But ocean currents are fast. The math must constantly outcase the hardware.
It is a worst-case scenario for saturation. But the results were stunning. They proved that by adding just a single tuning parameter to these simple classical models, the back calculation allowed the AUV to achieve maneuver tracking performance that was entirely comparable to the highly complex, computationally exhausting MPC models. The classical models kept the submarine perfectly stable and prevented windup, but they did it with a fraction of the computational strain on the sub's embedded processors. It is a beautiful example of using simple, elegant logic to defeat brute force physics.
What a journey. We have traveled from the very edge of the machine's physical interface to the deep heart of its mathematical logic and back out to the brutal reality of its physical actions. We started with the tactile senses, understanding how a 16-bit absolute encoder uses gray code to slice a single rotation into 65,000 distinct digital addresses without glitching.
We pushed those digital signals across the noisy, chaotic physical layer of a CAN bus, relying on the physics of differential signaling to erase magnetic spikes, and using dominant zero arbitration to ensure the most critical messages survived the storm.
We arrived at the microcontroller, where the raw, jagged data was smoothed by the predictive mathematics of a Kalman, filtered dynamically scaling its own trust matrices to find the absolute truth hidden beneath thermal noise and physical shockwaves.
And finally, we acted upon that truth. We deployed a PID controller, battling the unyielding limits of actuator saturation, using back calculation to bleed off integrator windup, desperately keeping the pure math anchored to the unforgiving reality of the hardware.
Why should you, listening to this, care about any of this invisible architecture? Because this is the foundation of the automated world you live in. Whether it is the adaptive cruise control in your car dynamically braking to avoid a collision, the smart thermostat in your living room calculating the thermal inertia of your house, or an industrial robotic arm meticulously assembling the smartphone you hold in your hand, you now understand the complex conversations keeping those machines stable. You know the millimeter wars fought over resistors on their circuit boards and the mathematical safeguards preventing them from literally tearing themselves apart.
It really pushes the boundaries of how we define perception and control. Throughout this deep dive, we have framed sensor fusion heavily around biological analogies. We talked about blending the inner ear of an IMU with the eyes of a camera. We relate machine senses to human senses because it is comfortable. But machines are fundamentally not limited by biology.
That is a fascinating point. A robot doesn't have to stop at 5 senses.
This raises a profound question to think about. What happens as we begin to deeply, seamlessly integrate completely non-human senses into these predictive control loops? We are already mounting high-resolution thermal imaging, ultrasonic echolocation, and hypersensitive electromagnetic field detection onto single autonomous platforms. When a single robotic intelligence is tasked with fusing visual light, the pull of gravity, invisible thermal signatures, and local magnetic variations into one unified predictive worldview, will the Kalman filters and neural networks required to balance those alien senses eventually evolve into a new, purely artificial form of intuition, a way of perceiving and predicting the universe that human biology fundamentally cannot comprehend?
That is a staggering thought to leave on. It brings us right back to that master pianist we talked about at the very beginning. The biological loop of perception and action is a miracle. but we are actively building a completely different kind of nervous system out of silicon, copper, and code. And maybe, eventually, it will play a tune we can't even perceive. Thank you for joining us on this journey. Keep questioning the automated systems around you and keep exploring the incredible engineering hiding just beneath the surface of the physical world. Until next time.